Okay, so this is a special request from the internet, and some people have said I'm going to get bombarded, but I've only had, this is my second special request in about 9 months of doing this, so I'm not really overwhelmed just yet. Here's the problem. This happens in a lot of different textbooks. I've got an upper arm that is vertical, I've got a lower arm that is horizontal, I've got a mass that's in my hand, and we want to know what is the force in my bicep pulling up, and then also what's the force at the bone-on-bone joint. So I've got it set up for you here. Here, this is my bicep, and then right down in here is my bone-on-bone joint, and basically it's not attached. It's just I've got my C-clamps making little sockets so it doesn't go crazy on me. This here is my lower arm, and I added a little mass just to make things a little bit interesting. And right here is the mass. This would serve the function of the mass that's in the hand. So bicep, bone-on-bone joint, lower arm, mass in the hand. Okay, and we're going to come back in a second and do this on pencil and paper, but I just want you to take the measurements. So this is a real-world situation. I set it up in the lab. We're going to take the measurements, and then we're going to work it out on pencil and paper and see how it works. Okay, so first off, I look here, and I see that the tension in my bicep is going to be 31 newtons, and I've already gotten that written down, and my bicep is attached 14 centimeters from the pivot point. Next, what I want to do is I want to measure how much force these two surfaces are pushing on each other. So I've got another spring scale down here, and what I'm going to do is I'm going to pull on this spring scale just until I get a little bit of separation. So if I wait until I get a little bit of separation, so right there is where it separates, and I am at, well, I put down 17 newtons before. Let me flip this around. I can't really quite see. I had it on backwards. So my bone-on-bone I'm going to call it 19 newtons. And we're going to call this 0, so I'm going to say it's 19 newtons at 0 centimeters. And then out here, I've got a 500 gram mass. So that 500 gram mass is going to be providing 4.9 newtons of force, and I've got it set up at a distance of 65 centimeters from our pivot point. So I've got a torque here, a torque here, a torque here, and then the last thing we need to know is the center of mass of my forearm. So we're going to now dismantle everything, and we're just going to find the center of the mass of the forearm. Pull everything out. And here's my forearm. Now to find the center of mass of my forearm, I'm just going to let my fingers slide together, and the center of my mass of the forearm is going to come right there. I flip it over. It's 38 centimeters. So center of mass of my forearm is 38 centimeters, and then I previously measured, I have a scale here, and I previously measured that the mass of my forearm is 170 grams. So that's our data, and now let's go crunch some numbers. Alright, so we're back, and we're going to look at the following situation. We had my forearm, and we had sort of a bone-on-bone attachment here. And then we had a bicep. And then we had a center of mass. So this is a forearm. And then we had a weight in the hand. So we had a weight. So then what I figured out was that this was, I had a force here of 19 newtons at 0 centimeters, and then I had a force here of 31 newtons at 14 centimeters, and then I had, that was 170 grams, which I'm going to multiply by 9.81 meters per second squared. Let me just show you that. Oh, hang on a second. Gotta get into good practice mode. So 170 grams is going to be 0.170 kilograms times 9.81 meters per second squared. .7 newtons, so we'll call it, or 1.68 newtons, 1.67 at 38 centimeters. And then we had the weight in the hand was 500 grams, which is 0.5 kilograms. And so 0.5 kilograms times 9.81 meters per second squared gives me 4.9 newtons. Okay. So there's our data. Now what we're going to do is we're going to assume that we don't know this, and we're going to assume that we don't know this, because that's the way it goes in these typical problems. And so we're going to solve for the bicep first. Now the whole name of the game here is torque. And that's force times radius. And the other thing that I want you to understand is no rotation equals no net torque. And I'm going to introduce this symbol. This is, let's see, and then the last thing I want to do is, this is a Greek tau. This is the Greek letter tau, and it means, in this case, it means torque. Okay. So, in this case, I've got 4 torques. 1, 2, 3, 4. And if I add them all up, I should get 0, because as you saw, as you looked in the video, it was not rotating. So it was just stationary, so there's no rotation, so no net torque. So these 4 torques add up to 0. Okay, so .9 newtons at at 65 centimeters. Okay, so here's my problem. So I'm going to say torque 1, torque 2, torque 3, torque 4. Okay. So I'm going to say torque 1 plus torque 2 plus torque 3 plus torque 4 is going to equal 0. So now I'm going to say 4.9 newtons times 0.65 meters plus 1.67 newtons times 0.38 meters plus force 3 times 0.14 centimeters plus force 4 times 0 centimeters is equal to 0. Okay, well now this is something times 0, so this goes away. And so then I can manipulate this over to the other side, but I'll just sort of do it out. I'm going to do this as one number here. Right, so let's get that. And it's going to be 4.9 times 0.65 plus 1.67 times 0.38. So this whole thing here is going to be 3.82 Newton meters plus force 3 times 0.14 centimeters equals 0. Well, now I can say that force 3 is going to be equal to, I'll let you do a little bit of algebraic manipulation on that, 3.82 Newton meters divided by 0.014 meters. Oh, that should be meters right there. That should be meters right there. And so I calculate that my force 3 should be 27 newtons. Okay, so that's calculated. 31 newtons measured. It's not the best agreement that I've ever seen, but I'll take it. It's close enough. Then, take a little pause, and we'll come out and we'll figure out what the force is in that joint. So now we're going to we're going to calculate off of this data, we're going to calculate the force in the elbow joint. And we're going to do a little trick to make this happen. Now, on my ruler I had 0 centimeters, 14 centimeters, 38 centimeters, 65 centimeters. But I can put 0 wherever I want. So I'm going to do something really tricky. I'm going to redraw my situation. And I'm going to have torque 4 is going to be acting at negative 0.14 meters. Now I'm going to say that torque 3 is at 0 meters. Then I'm going to say torque 2 is going to be at, let's see, it's 38 minus 14. It's going to be at 38 minus 14. So that's going to be 24. So it's going to be at 0.24 meters. And then I'm going to say torque 1 is going to be at, that's 1.67 newtons. I still know that. Torque 1 is going to be 4.9 newtons at 65 minus 14 equals 51 centimeters. So 0.51 meters. Okay, So what I've done is I've shifted my 0 point. So instead of 0 being at the elbow, 0 is now at the bicep. Okay. Because I can actually just sort of set, it's just not rotating, so there is actually no pivot point. So I can really set 0 wherever I want it to be. So now let's write out our torque 1 plus torque 2 plus torque 3 plus torque 4 equals 0. And I'm going to get 4.9 newtons times 0.51 meters plus 1.67 newtons times 0.24 meters plus F3. We just calculated F3, but let's just ignore that we have it because it doesn't really matter, at 0 meters, because now that I've set that at 0 meters, if I botched the previous calculation and I got F3 wrong, it doesn't really matter because now whatever value for F3 is multiplied by 0 meters, and so that's going to just go away. Plus force 4 times negative 0.14 meters equals 0. Okay. So now, again, we'll do this on this side. So I did 4.9 times 0.51 plus 1.67 times 0.24, and I get 2.9 Newton meters, and then I'm going to have minus 0.14 meters times F4. Some of you are going to notice, this is sort of bothering me. Some of you are going to notice, they're going to say, wait. When you solve this, you should come up with a negative. So actually, I went a little bit too fast, and I actually should get a negative. And the negative makes sense from the diagram, because if you see, if I say that this is positive, this is a positive force, this is a positive force, this is a positive force, well, this one's going in the opposite direction. So I got my upper arm pushing down on the elbow, I've got the weight of the arm pulled down by gravity, I've got the mass in the hand pulled down by gravity, and then the bicep is pulling everything up. So positive, 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 negative. So that should be negative. I just wanted to know the force in the bicep, so I didn't really worry about positive or negative. Okay. But so if we go back to this one, then we're going to get a positive force. So I'm going to say F4 is going to be equal to 2.9 Newton meters divided by 0.14 meters, and I'm going to come up with 20.7 newtons, and that is my calculated. And we'll go back, and my actual was 19 newtons actual. Okay, so in both cases, so if I go 20.7 divided by 19, I get about 9% error. And if I go 31 divided by 27, I get about 15% error. So I just kind of threw this together on a Saturday morning for a web viewer, and I came up with 9% error and 15% error, and I'm happy with that. So, bottom line, the torques are all equal. I'm sorry, the torques all sum to 0. And so this torque plus this torque plus this torque plus this torque all added together equals 0. I can set 0 centimeters wherever I want, etc., etc. You can go back and watch the video. If you have any questions, you can send me an email. Bye-bye.